Good morning, this is your stats sensei, and we're going to be going over two sample proportion confidence intervals. Take a real quick look at some claims and things we can say about confidence intervals, but by now I'm assuming we have a fairly good understanding of what a confidence interval is. So not going to spend a whole lot of time on this, so you probably should pause the video to read what is on this page, because this page is loaded with important information. But first off, the purpose is to create a plausible range for the difference between the population proportions of two independent populations. All right. So trying to find the plausible range. And basically that's saying that we're going to be finding a difference, which means we're going to be subtracting. And of course, we'll use sample proportions. And this will be shown as p hat 1 minus p hat 2. We'll be finding our difference. And with a confidence interval, it's always the estimate plus or minus the margin of error. The estimate is p hat 1 plus minus p hat 2. And then everything after that, after the plus or minus, is the margin of error. So the part that I'm underlining right here would be the margin of error formula. And then if you drop off the z, we have what is known as our standard error. And that's p hat 1, q hat 1 over n1 plus p hat 2, q hat 2 over n2. And please note that when I use a q, that really just means 1 minus p, and I'm using the q hat just because it takes up a lot less space. All right. It's real important that you know the difference between margin of error and standard error. And you got to know that the margin of error includes the z, standard error does not, but that works the way it has with all confidence intervals at this point. Okay, so the purpose is we don't know the difference. We don't know P1 minus P2. In other words, we don't know the true population parameter. So we're trying to estimate it using this. And so we're using the sample proportions. Remember, when we use a hat, we're talking about sample proportions. Without a hat, we're talking about the population proportion. So this is population. This is the sample. Okay. P hat is equivalent to saying X bar, and P is equivalent to saying mu when we're talking about means. So these were our symbols for our means. This is our sample statistic. This is a sample statistic. This is a population parameter, and this is what we're trying to estimate. All right. Obviously, if I square this part, the standard error, I end up with the variance. All right. Not that exciting, etc. Our claims are the same. I'm not going to take the time to read them because we've been using them over and over again. I do want to caution you, please do not combine those statements. Do not, we can claim we're 95% confident or in repeated sampling, but do not combine those claims. It makes a mess. So if it's a multiple choice and they've combined them together, that's almost guaranteed not to be your answer. All right. Please note, we always are making the claim about a population. So the claim is about the population. It is never about the sample. If the sample is in the multiple choice, it's wrong. We are always making the claim about the population. We know what the sample is. We know what the sample's difference is. The sample difference is exactly that value. But what we're trying to estimate is this, and we're estimating this using this formula right here. Okay. These are the things we cannot claim, the reasons we can't claim them, or some of the reasons we cannot claim them. Once again, I'm not going to read them because, again, this is something that we've dealt with in the other videos, and basically you might want to pause the video here and read this, but I'm not going to go through them step by step on this. Remember, again, as I said above, the purpose of the interval is to provide a range of values for the parameter. In our case, the parameter that we're trying to find the range of values is P1 minus P2, the difference in the population parameters. Please note, just like the same as before, if the null lies within an interval, there's not enough evidence to reject the null. The result is not significant. So if they ask you if the result is significant and their claim lies within the interval, within the confidence interval, it's not statistically significant. We can say it's plausible, that the null is plausible at that point. So in other words, we can say if the claim lies within the interval, there's not enough evidence to reject it, the null is plausible. All right. Please note that I said the null is plausible, not the alternative. All right. All confidence intervals are two-tailed, and alpha is in the tail. And when we're looking at a picture of that, it's something like this. Nothing is different, but alpha over 2 is in this tail, and alpha over 2 is in this tail, and together they make alpha. Together they make alpha. All right. I'm just going to tell you, this is extremely important in regards to multiple choice questions. Please know the way the interval changes. So as we increase the confidence level, the margin of error increases and the interval width increases. As we increase alpha, the margin of error and our confidence interval goes down. As we increase the sample size, margin of error decreases. All right, consequently, the interval width decreases. As we increase the standard deviation or the standard error, the margin of error increases and the interval width increases. I don't think that's a surprise there. And finally, because we have only sample data, we are never able to say with exact confidence what the difference, we're never able to say what the exact difference in the population proportion or means is. Will never be 100%. We're just estimating it. And that's why we have a range of values. So the range of values is the plus or minus part, the margin of error. But our best singular guess would be p hat 1 minus p hat 2 is our best guess, but it falls within the range of plus or minus the margin of error. All right. Okay, so with our recipe, again, I'm going to go through this rapidly because we've done these before. There's not a whole lot of difference here. We need to make sure we define P1 and P2 in context for both of them. All right. As far as conditions, we need to do them for both. So we need random samples. We need independent samples. And by the way, whenever we're working with, when does this come into play? Anytime we have two separate groups, all right? So anytime there's two, and they need to be independent. With means, we needed two independent groups for the means. Even if it was a paired, the differences needed to be independent. So one group, one difference paired was different from the next paired. So that's where independence comes in. So it's only added when we're working with groups of two. All right. We need to have a sample less than 10% of the population. And this right here is our normality condition. All right. And this basically says that whether or not we can use the normal approximation, because technically we're working with proportions, and proportions are really a binomial. But if our sample size is large enough, we go, you know what, it's close to normal, we can go ahead and use it. So this is our equation. Please note that in the standard error, we're using p hat. The reason we're using p hat is because we don't know, we don't have a claim for the null, so we have to use the sample. Remember, just as in one sample, p hat is x over n, the number of successes over the sample size. All right. Everything else follows the same. And we're looking for, we are 95% confident that the differences in the true population proportion lie within the interval blank. All right. So one last thing. If 0 is in the interval, there's no significant difference. If 0 is not in the interval, there is a significant difference. I don't think anything here is substantially different than what we've expected. So let's go ahead and begin our first scenario. So scenario 1, a grocery store manager notes in a simple random sample of 85 people, that's interesting, going through the express line that only 10 paid with checks. So if 10 paid with checks, 75 did not. in a simple random sample of 92 customers. Hey, we have two groups. We have two groups passing through the regular line, 37 paid with checks. Construct a 95% confidence interval for the difference. Now you may be saying to yourself, well, they're asking for the difference and I know that, but how do I know this is a proportion, or how do I know if this is a mean? And that's a really good question. But when I look at this, I don't see anything that mentions mean. I don't see anything that mentions average. I do not see anything that says X bar. So I don't think this is going to be something about a mean. But what I could do is I could make a ratio, because I could be sitting there and going, you know what? P hat 1 equals 10 over 85. Well, that's a ratio. So I can set up a ratio or a percent or a proportion. And if I can do that, I can do the proportion test. And with P hat 2 equals 37 over 92. So it looks like I can set up two ratios fairly easily. So consequently, there we go. I can do a two proportion test. And there are times you can run a test for means, but here we don't have really anything that indicates X bar, but I definitely can set up two ratios. So my null hypothesis is P1 equals P2. It could be written also, and please note you need to be able to recognize this for multiple choice purposes, or even FRQ that sometimes they write it this way, P1 minus P2 equals 0. Notice I'm using the population notation. I do not use P hat. We never use P hat. We never use sample notation for our null and alternative, because we're making claims about this. And then our alternative, and they're looking for a difference. And the reason I know that is because it's a confidence interval. Now technically, I don't even have to do this, but sometimes it helps students understand that all confidence intervals are 2. Now, what this says is P1 is the true population proportion of people paying by check in the express line, and P2 is people paying by check in the regular line. And I really could restate these as P1 true I could look at this and I go, true population proportion of people paying by check in the express line equals the true population proportion of people paying by check in the regular line. Or alternatively, the true population proportion of people paying by check in the express line is not the same, or is different, or is not equal to the true population proportion of people paying by check in the regular line. All right, so my conditions up above, they told me that I had two separate random samples. That's great. So random sample for both is given. All right. Reasonable to assume independence, as one line should not impact the other. And by the way, this should be marked as 2, and the following things should be marked as 3. Then we need to check NP and NQ. Well, in this case, they told me that they had 10 people paying with checks in the express line. Or I'm sorry, we're not to NP and NQ. We need to check sample size. The N is less than 10%. So 85 divided by 0.1 is 850. Reasonable to assume that more than 850 customers use the express line. And 92 divided by 0.1, 920. And it's reasonable to assume that more than 920 use the regular line. Please remember, we can go 92 times 10, and we can go 85 times 10 if you prefer to do that as opposed to the division. All right. So in both cases, our sample size is less than 10% of the population. All right. Then we have NP. Well, our sample is 10, and that happens to be greater than or equal to 10. So that condition is met. And then the 75, well, we had a sample size of 85, and 85 minus 10 is 75. That's also equal to 10. So that condition is met. Then we had, for the other proportion, we had 37 paid with a check. All right, and that's greater than or equal to 10. And then if we take the 92 minus the 37, well, that's 55, and that's greater than 10. And we have to meet all 4 of these, and we have to show that for all of them, both samples are large enough to use the normal approximation. So both samples are large enough to use the normal approximation. So we're good there. So we write down our formula, and we know that p hat 1 is 10 divided by 85. And if that's 10 divided by 85, then q hat 1 is 1 minus that, which is 0.8824. P hat 2, we had 37 who paid with check going through the regular line, which 1 minus that is how many paid, or is the proportion who paid in the express line. All right, so I can plug into the formulas, and sometimes my students will want to plug in and they'll go, you know what? I want to plug in 10 over 85 for P hat 1, and then plug in 75 over 85 for Q hat 1. Then over here, they'd plug in 37 over 92 for P hat 2, and then they would plug in 55 over 92 for Q hat 2. You're welcome to do that. You don't have to use the decimals, and actually, it's probably, that is more accurate. I choose not to do it because it's hard for me to be that neat. However, it is more accurate. So if you want to use the decimal version or the fractional version, that's fine. Either one of those is accepted. And the same with that here. P hat 1, we could have put in right here, I could have written 10 over 85. And over here, I could have written minus 55 over, or not 55, 37 over 92. I could use that as well. So let's go ahead and start plugging in. So we're going to go stat test. And I got a bunch of bad glare on this. There we go. That helps a little bit. Stats test. We're going to have to scroll down. I believe it's to letter B. To proportion Z interval. And by the way, since we're working with proportions, it's always a Z. And what did we have? Well, we said that our X value was 10 and our N was 85. Once again, these must be whole numbers. If they're not, you're going to have to round to the nearest. All right. Then the other one was 37 over 92. And we wanted to conduct it asked us to construct a 95% confidence interval, so 0.95. And I end up getting a negative value. Why? Because more people use checks in the regular line than used in the express line. And both of the values we get are negative. So 0 is not in there. So that means the difference is significant. All right. Now, the one thing we haven't talked about is how to get our Z star. Well, that's no different than what we've done before. That's going to be second vars, inverse norm, parenthesis, 1 minus 0.95, close parenthesis, divided by 2. Mean is 0, standard deviation of 1, because we're working with a Z-score. So there's our 1.96, and that's where that came from. Always have to have that and make sure that you have the right value. If you don't, you're going to get knocked down to a partial, all right, or possibly no credit. But this will be work shown. So what can we say? We are 95% confident that the differences in the true population proportion between those paying by check in the express line and the regular lines lie within an interval this. Now, if you wanted to write this as express minus regular, you could do that, but I need make sure that you explain what it is that you're doing. And in repeated sampling, we expect that our method will capture the true population proportion in the difference from those paying by check in the express line and regular line 95% of the time. And finally, we need to make a summary statement. We notice 0 is not in the interval, therefore the difference is significant. And we also note, this is important, because the interval is negative, we know that there's a greater proportion of people paying by check in the regular line. And because what we showed is not only was there a difference, but it was statistically significant. right? We said it was statistically significant at the 95% level, confidence level. By the way, just as a commentary, paying by check in the express line or using coupons, you're an inconsiderate jerk. Do not, going through the express line, don't use checks, don't use coupons in the express line. You're welcome. That was a life tip. It was for free. Probably won't be on the AP exam, but it may help you out anyway. Thank you a lot for watching, and I hope you'll catch me on the next scenario. Well, guess what? Sometimes I have trouble getting the things to stop. So this is going to drag on just a moment.